All right, here we are live. Thank you all for joining in on this lesson on database management. That's what we're going to be talking about through these lessons. Uh, we're going to look at, you know, how or what a database is, how it's structured and designed, and then we will get into the SQL language so we can learn how to actually interact with the database, build a database, update it, maintain it, get data from it, all the stuff. Okay, and in these lessons, like all the other lessons that I've done, uh, it's more of an overview, and it is foundational material. It is not exhaustive or extensive. Um, if you want to learn more about any of these things that we cover, then you'll definitely need to play around with the stuff and also go and explore the documentation uh, for all these coding techniques and languages and frameworks and everything else that we discuss, all these concepts. And I believe in these slides, if I'm not mistaken, we have references to all of uh, the online resources that are out there, so you have access to it. If you want to learn more, if you just want to, you know, learn whatever I teach you and that be it, then so be it. Uh, Va con Dios. Anyway, let's get into database management. Let's get this show started. Uh, here's the information, well, the table of contents, if you will. Again, we're going to look at introduction to database management, then different database systems, then introduction to SQL or SQL. Look at schema and tables, what that means, SQL data types, and then we'll look at CRUD, which stands for create, retrieve, update, delete, join, and then case. So that's all the stuff that is in these slides. And these slides I will make available in the um, classroom stream. All right, here we go. Now that we've discovered, the front end of full stack web development, it's time to put our focus on the back end. And we'll revisit the front end later, and we shall. So far, with what we've covered, our websites are pretty static, meaning that much of what is displayed on the browser has to be hard coded, right? Everything that we've done on the front end, if it's, some text, images, whatever, all that is hard coded. We have to write the code for it somewhere in a file, right? Um, and JavaScript allows for some dynamic activity, meaning as what gets displayed, when it gets displayed, or whatever. Um, However, it's not efficient for scaling our websites, and that's what we want to think about. We want to think about how to make these web applications scalable, and the model that we've been using thus far, while it works, is good, and for something small, it's okay. But if we want to make our web applications scalable, we have to think differently about it. So to improve our websites, we want to set them up to where they are data driven. What this means is that the data that we have will ultimately dictate what is displayed and how. That's the world we want to live in. Okay. So the idea, the concept that we have is that our on the front end, we're more focused on creating templates, like a basic structure of how we want our data to be displayed for the client. However, we want this to be driven by the data, which is stored somewhere else. Okay, and that's the world we want to live in. So have our data, however much data we have, that ultimately dictates what's displayed on the browser. I mean, you can think about you know the big days out there, such as like say Netflix or any kind of streaming channel or platform or social media applications that we use. Uh, the they could not survive if they structured their uh, applications based on like maybe 10, 15 users or what have you. They just couldn't make it like that. If Netflix said, we only have 8 movies, so um, the way it will function will be much differently. But we have, they have such large sets of data that they need to format it in a different way. And so while this lesson isn't going to get you into Netflix, I don't think, and if it should, the Netflix definitely needs to hire me. Um, but it should like give you an idea of how these things work and how we need to think, how we should approach our development work moving forward. To allow this, we need to store our data in a systematic way that organizes and normalizes it, making it accessible. This data storage is done by building and managing a database. What is a database, you ask? A database is a set of related information. That's it. You can think of the contacts in your phone as a database, and that's what it is. For example, each contact will have a name, preferably a first and last name, at least one phone number, an email address, perhaps even a physical address and birth date. We can also store an image for your contact. Also, we can with where our phones are now, we can obviously we can give them a certain ring or notification alert. The was it the sound haptic? Your phone will vibrate a certain way. You could set that for a particular contact. You can favorite a contact or unfavorite them. Uh, you can do other things, right? So there's a lot of stuff that we could do in a phone contact. So the way that this information is stored, it helps us to locate it as needed, and it makes our experience as smartphone owners more enjoyable. Right, gone are the days where uh, probably you all's grandparents, maybe your parents, maybe I don't know, but definitely like your grandparents uh, had to write down numbers. They have like a journal, and they would write down phone names and phone numbers for people that they meet, or people that they numbers they need to have. Also, there were phone books back then, and I think they still kind of drop those off every now and then. I got one. I don't think it was last year, maybe year before. I was just shocked. I was like, "Wait a minute, what is this? The actual phone book at my doorstep, huh?"
I feel like it's good to still have them around.
I do too, but it's just
For your landline, if you have one.
or for sitting down on it if you're too short in a vehicle. But yeah, we those things are pretty much obsolete now because of what smartphones can do now. And again, this goes into like having a database. So in your phone, you're creating a database of contacts, people that um, you call. All right. So when we talk about databases, there are two overarching systems that govern how databases are structured. We have the non-relational database and we have the relational database. And let's look at non-relational. A non-relational database is one which does not use tables as a part of its schema. Instead, the data is stored in a manner that is best suited for the data itself. Some of the more popular non-relational databases you see here: MongoDB, Apache, Cassandra, and DynamoDB, which is ran by AWS. So, matter of fact, I think I have an example here. Here's what a non-relational database may look like. Okay, and so you see that this first entry, we have artist Miles Davis has an ID, title, duration, year released. They all have that, but we can see. I mean, what does it look like? Yeah, it looks like an array of objects exactly, and that's what it is. This is a non-relational database. Even though we can see here in this example that they all feature the artist Miles Davis. The data here, they're completely isolated from one another. Okay. This is a non, there's no way to connect one piece of information to another. Um, the information is completely separate in this kind of format. This is a non-relational database. It looks like this. I believe the Mongo DB, I believe, looks like something like this. Another thing with non-relational databases, and it's not shown here on the slides, but they don't all have to have the same properties, if you will. Uh, let's say for the first entry with the title of kind of blue, I could add another property in there. I don't know, maybe is favorite or uh, a list of the ensemble for this album. I could do I could do several different things, and I could do it for that entry and not do it for the other ones. So again, with a non-relational database, they don't all have to have the same keys or properties, if you will. They can be completely mutually exclusive from each other. So that's a non-relational database. And so, yeah, if you want to explore some non-relational databases, I recommend that you do that. I know I definitely want to dive into uh, at least one of them uh, just to expand my knowledge. Let's look at relational databases. A relational database is one that is built using tables made up of columns and rows. This model is structured so that the tables relate to each other by using redundant data to link them. So if we go back here and look at this example of the non-relational, it is not made up of tables or rows and columns. It is just it's key value pairs in this instance right here. And I believe most non-relational databases are formatted this way. Um, but is there key value pairs with a non-relational database? And it looks similar to what we've been doing with JavaScript. It looks like a JavaScript object. So I can certainly understand why someone will want to use this kind of system because you're just familiar with it. Right. But let's look at the same information displayed as a relational database. Okay. And so here what we have is two tables. We have one table for the artist and we have one table for the album. And we can see that each one is made up of rows and columns. The rows are horizontal, columns are vertical, and we see that we have the uh, each table has what's called a field, and that's what that label is at the very top row. where we have like artist ID and then artist and album ID, artist ID, title, duration, year release, etc. Uh, those are fields, and then our entries here are listed below. So we have like, uh, if we look at artist ID in the artist table 001, and it's Miles Davis, and then we look at artist ID in the album table, and it has 001, which means that what it does is it points to the artist table and makes a reference to the artist table saying, hey, whichever entry you have for the ID of 001, that's who we are referring to here in the artist ID field. So the same information that was displayed in the artist in the non-relational database, this is what it looks like in a relational database. Okay. As with other languages and frameworks in programming, there is no right or wrong path to choose, and there really is not. Do not listen to the people who think that there is one supreme coding or programming language. There is not. Uh, you do what you have to do to get the best results, okay, for whatever it is that you are doing. Uh, yeah, there is no one that's better than the other. But in this lesson, we're going to be using a relational database system, and we're going to be learning SQL. Okay, so that's what we're going to be doing here. The structured query language, or SQL for short, is a programming language used specifically for database management in a relational database system. It was developed in 1974 by Donald Chamberlain and Raymond Boyce, those two fine gentlemen, wherever they may be. Um, there are several different classes of SQL statements in the SQL language. We'll focus on two. We're going to look at schema statements and data statements. Okay, these are the two that we're focused on. So you need to kind of hold on to this, please. Focus on this because this is this will be on the pop quiz. Schema statements are used to define the data structures. In other words, how we build the database and schematically organize our tables for optimal use. The schema of the database. All right, we use schema statements for that. So you can think of it as how this database is built, um, how it is organized, how our tables point to one another and connect, just that overall mind, if you will, of the database. That is what our schema statements uh, define. And then we have our data statements. And data statements are used to handle and manipulate the data. How do we get the data from the database? How we store data into the database? You know, what if we need to make some kind of change to the data? You know, maybe something gets updated, and when does it get updated? You know, all these different things. That is what the data statements uh, define. So these are the two concepts we'll have when it comes to writing out SQL: uh, schema statements and data statements. All right. The schema. What is the schema? The schema is the model that is used to not only build the tables, but how they connect and interact with each other, like I just mentioned. In relational databases, tables are linked together by repeating data. Let's take a look at some tables. Uh, a table, as we have here, this is a set of rows and columns. That's all that a table is. So when you hear someone say table, we're referring to a set of rows and columns. Each row represents a set of columns that completely describe what we call an entity. And each column represents a single piece of data that is stored. The column has a header which specifies the data that is listed. So here we have some dummy data. You see that each column has a header, ID, first name, last name, position, salary, and date created. And then each row has its own entity. So this row with the ID of 001, this represents this data here is completely separate from the data that is below it. We said that is a completely different entity. This Lisa Jones, that that information is completely separate from that of Mark Smith. Can we see that? Yes, we can see it. Great. The intersection of a row and column creates a cell or field. Our data rests within these fields. For optimum performance, there are three rules regarding the entries in our fields that guide how we build our tables. And we kind of talked about this earlier. Number one, each field contains one and it should be one and only one piece of information. So each field contains one and only one piece of information, meaning that you cannot have two pieces of information in the same field. Um, what is the flavor of this pasta? It is savory and spicy. You can't do that. One piece of information in each one. Two, there should be no redundant fields or no repeating data. Don't put the same entry twice. Get it? Never mind. Each table, the third one, well, let's go back to that. No redundant fields, okay? Meaning again, we don't want to display information uh over and over again in the same uh column. Three, each table includes a unique identifier in each row, also known as a primary key. This is how we are able to uh, separate the entries from one another, and that they all have a unique identifier. Okay, um, the basic one we use is ID. You give each uh each entry an ID, similar to what we did when we had an array of objects in JavaScript, uh, and that separates that makes each entry separate from the other, and you'll see that that's how we're able to access information easily by having a unique identifier. And we call this a primary key. Okay, so when you hear primary key, that's what we're referring to, the unique identifier. So, uh, whenever you're building out your data models and then your database, keep these rules in mind. All right, let's move forward. As with other programming languages, SQL has its own data types. Many of them very similar to the ones that we've already covered. Uh, SQL data types are grouped into three categories. We have character data, we have numerical data, and we have temporal data. Character data. Character data can be fixed length or variable length strings. A fixed length string looks like this. We use the char keyword, and in parentheses, we have a number, like right here, char2, which it could be used for something like state abbreviations. Then we have char9, which could be used for like the social security number. So anytime you have a fixed length, meaning that each entry has to be this many characters, you will use the char data type. A variable length string looks like this. We use varchar, and then we specify a number. So this represents any set of up to 40 characters in this example that we have here. So we have char, varchar. Um, when choosing data types, we must be mindful of the storage space each one requires. The max length for char is 255 bytes. For varchar, 65,535 bytes. And sometimes we may need more space, like say we need space for a blog, or like here we have description of a movie, in which case we will use the text types. So if you think about like say IMDb, and they'll have the plot of the movie listed, you would need something larger than varchar. Need a little more space in that. So we could use one of these text types. We could use tiny text, text, medium text, or long text, and you see how big the storage is. Okay. So when it comes to this, what we don't want to do is just, apply long text to everything just to be lazy, because you are actually setting up how much space you actually need. And you don't want to just take up a whole bunch of space, right? Because that is space you are taking away from, something else, or you're just not using it, meaning it's not efficient. If you can think about having, say, a refrigerator at home, and you only have one tomato and one lemon in your refrigerator. Some people don't even put lemons in refrigerators. Uh, I have no thoughts about that one way or the other. But the point is, it doesn't make sense to have this large refrigerator with only two pieces of fruit, and yes, tomatoes are fruit, inside of your refrigerator. Um, that is just, you're just wasting energy there. And so that concept is the exact same when it comes to your database. Please don't just, you know, give everything long text. Just use the maximum space that you can if you don't need it. That is very inefficient. SQL provides another character data type called enum. Enum adds a constraint to the data that can be selected. For example, if we wanted to add a rating to a movie database, there are only a handful of ratings, and we can constrain the data to ensure that no erroneous information is entered. And you see here the example. We use enum, and then in parentheses we list out what, and so we don't want to do that. So next we have numeric data. Numeric data type is for storing numbers that can be calculated. This is different from previous social security number example, because in that example, social security number, we don't do any calculation with the social security number. It is simply a number or a code that identifies every American. But like character and text, numeric data can either be signed. Well, this should be unlike. Uh, Numeric data can either be signed, positive or negative, or unsigned, which means only positive. Um, and like text, numeric data is broken up into different categories to account for the size of data. So I got to clean your slides up because, yeah, character data can be signed or unsigned. However, numeric data can. So we use positive or negative integers, or we can set up to unsigned where it only accepts positive integers. Let's look at the numeric data types. We have tiny int, which is unsigned. It is 0 to 255, and signed it is negative 128 to 127. And in small int, negative 32,768 to 32,767, or 0 to 65,535. Then we have medium int, and you see the range for that int and big int. So when to apply these, because again, what we don't want to do is just use big int for everything. Uh, if our data, like say, I'm doing a database of NHL teams, um, I believe there's 32, 33, something like that, maybe a few more. What I don't want to do is use small int for that. That doesn't make sense because there's not going to be 65,000 NHL teams. Um, tiny int would be sufficient. So yeah, I would use that. I think one of the examples we looked at is if we wanted to record um, extreme temperatures in the globe. Signed range for tiny int would almost cut it. I think what was it? Death Valley was like 134 degrees or 128.5, something like that, just right outside of the range that kind of messed it up. Excuse me. Um, but that we wouldn't be able to use that. Um, but let's say small int. I mean, we would have to use it for that. Small int could be used for um, say want to have a database from like maybe for a store, um, a brick and mortar store. Certainly not going to carry 65,000 items, but I believe they definitely would carry, depending on the store, would carry more than 255 products. So you want to use small int for that. Medium int could represent, maybe a population of some states, not all the states, because there's a California and New York, but most states you could do that. I don't think that there's 16. Well, definitely not 16 million cities. Yes.
So for NHL, or just to go back for a second, could you use small int if you're listing the players on each team?
Yes, if you listen the players on each team, for every single player, in the history of the league, yes, but not.
I feel like if you
Well,
use
yeah, you would need
small,
it for all the you would small int would be the thing to use. Yes, yeah, definitely, because there's not more than 200. Well, there's more than 255 players.
yeah, that's
Yeah,
probably like two teams right there.
no, not two teams, maybe eight or nine,
But
but
still,
yeah, but not So yeah, you would use small int for like the players, and I looked it up on a web application that I'm was it Sports Reference, and they list out the total number of players like in the history of the sport, and believe it or not, I think small int would cover most of them. I mean, even like baseball, which is well over 100 years old. um I think now in the future, next 10, 15 years, definitely
yeah,
it would need to be updated if it's not already to medium int, but uh small int covers it. And it's just interesting how you see um the ranges and how extreme they are. You go from 0 to 255 and then 0 to 65,535, and then from that
like
to 16
18
million.
million.
But there's a formula, and we can kind of see when we look at big int, it's based on this formula that we have here, and that's where these values come from. Because I believe that 255 is 2 to the, I want to say, eighth power minus one.
I think so.
Um, and then 65,000, that would be what, 2 to the 16th power, I believe. Uh, minus one, so on and so forth. I don't know off the top of my head. I should probably know that. But, anyways, You see here are the ranges, and you use whatever is necessary. Don't just, slap the big N on anything. All right. We're using integers. We with a decimal value, we'll use the float type. For example, we want to store the price of an item in the store. Let's say that everything in the store will cost less than $1,000. To store the price of an item, we will say float 52. This means that there will be a total of 5 digits with two of them on the right side of the decimal point. So if I say float 52, the greatest value that I can have is 999.99. So that is the float data type that goes along with numerical data. And then lastly, we have temporal data. Temporal data refers to dates and times. Here we see date, and its format is year, month, day. And you see the values, the range. It goes from January 1st, 1000 to December 31st, 99.99. And we'll still be waiting on a Frank Ocean album. But next is the date time. And the date time just adds the hours, minutes, and seconds to date. And next we have timestamp, which is formatted, looks like date time. The difference is with timestamp uh, is the range. The range goes from January 1st, 1970 to January 18th, 2038. And on January 19th, 2038, I don't know what will happen with that. I suppose that there'd be some smart individuals who would have that taken care of by then. Otherwise, it'll be like Y2K. What a time that was. You all weren't there. Well, some of you, one of you at least, was there with me, right? In that time when they were like, oh, the world's going to come to an end. Get some batteries and some bottled water and flashlights. Just bunker down. And everybody's just sitting there waiting on December 31st, 1999, just like watching TV, just wait for everything to explode, and nothing happens. Yeah. What a time that was. What a time that was. We were all afraid though. No, I'm not gonna say we all were afraid. It was just interesting. The Y2K glitch. Next is the year. The year goes from 1901 to 2155. So again, I assume that by that time, they'll have that figured out. And then time, which goes from negative. This is an elapsed time, so negative 838 hours 59 minutes 59 seconds to 838 hours 59 minutes and 59 seconds. Here's the components for the data types we just looked at. Again, year 1000 to 99.99. Month goes from 01 to 12. Day goes from 01 to 31. Hour from 0 or 12 o'clock midnight to 23, which is 11 o'clock p.m. So using, was it military time? That's what I guess is what we call it here. Hours, minutes, and seconds. So these are all of the different components for temporal data types. All right, so I'm going to pause here with these videos, digest this information, and then we're going to start looking at going into SQL and how to actually put this stuff into place. So see you on the other side of this video.
Coach, I just did the conversion